All right, I think it's time. Welcome back. We are going to continue talking about the isoperimetric quotient, and actually this will be the last day about gerrymandering, and this is actually the end of our, big, I suppose from the very beginning of the semester, we've just been talking about some things related to politics and democracy the whole time. This is it. We're going to get on to something completely different after we finish talking about the isoperimetric quotient. Remember, this is meant to be another measure of how weird a shape is, and this is the one which has to do with the perimeter. You can see the word perimeter in there somewhere. A little fun fact, just like the efficiency gap, for measuring how fair the districts are, the isoperimetric quotient is also used often in real life. In real life politics, actually they don't call it that. This is kind of like the mathematician's name for this thing. In real life politics, this is called this is just named after some people. The Paulsby-Popper. These are two different people's names. The Paulsby-Popper score is what they call it in real life politics. So if you see this, if you're reading in articles about gerrymandering, they might often refer to the Paulsby-Popper score. And apparently this Paulsby and Popper were actually two, this is strange but true fact. This is from a research paper in paleontology. Dinosaur bones, guys. This was in the from a paleontology paper in 1927. I guess those people care a lot about the shapes. It's all about how weird shapes are. Paleontologists care a lot about the shapes of sand grains when they're digging up the bones or something. And so there was some research done by some paleontologists about certain types of sand grains have weird shapes and other types of sand has normal shapes, and they came up with this basic idea which we use now in many other settings. This is one of those things that was invented and reinvented by several people throughout history. Paulsby and Popper were one of them. Anyway, like I said last time, this is basically area divided by perimeter. This is what I said at the end last time. Although it's not exactly that, but the basic idea is if I have two shapes, sorry, scrolling here. If I have one shape, that's a fairly nice shape, but here is a shape of roughly the same area, but a much bigger perimeter, right? That's how I'm trying to draw these. I actually don't know if these have the same area or not, but I'm trying to draw a shape which has basically the same area as that, but a much bigger perimeter. This would be regarded as, so this is a bad shape. This is a good shape. And the principal difference between them is that the bad one has much more perimeter than the good one, all right? And if you put the perimeter as the denominator in the fraction, that will make this fraction for this one over here, this fraction is close to 0 because it has a huge denominator, whereas this one is not close to 0 because the perimeter is not so big. That's the basic idea here. There's a problem though, so let's just talk about this. Maybe just as a shorthand, I'll write the perimeter as A, the area as A, and the perimeter as P, just so we don't have to keep on writing those words. So I'm going to say actually, this fraction here, A divided by P, is not great mathematically. Maybe I'll say geometrically. And I'll tell you what I mean by that. For example, what is this let's just take an easiest example I could think of would be a square. If I have a square, and let's just say it's a unit square, meaning the length of each side of the square is just 1. So this is 1, this is 1, this is 1, all right? This is the unit square. What would be area divided by perimeter? Well, here the area. Anybody remember? You don't have to be a super genius. Do you remember how to find the area of a square like this? What's the area? You could show me on the fingers. You remember I'm sure you learned the area of a rectangle formula. I see somebody is showing me on the fingers. Yes, it's this finger, the one. The area of a rectangle is always, the length times the width or whatever. The width times the height. And here, the length of one side is just 1. If it's a square, then the area is equal to the length of the side squared. That's why we call it squared. 1 times 1. So here, the area is 1 times 1, which would be 1. And the perimeter, I hope everybody remembers, the word perimeter means the total distance around the outside edge. Anybody think you can say? Show me the fingers for the perimeter here. I see some fingers. Some of you have not gotten your fingers out yet today. It's 4, right? That's just the total distance around the square. All right, so the area divided by the perimeter here would be 1/4, right? No problem. Here's what I wanted to say. I said area divided by perimeter is not great geometrically. Here's what I mean by that. What about, how about the same shape but bigger? How about like a big square? This is not exactly to scale with the first one, but let's imagine a square that has length 10 on each side, all right? Now this is the same shape, so whatever measurement of how weird the shape is, it'll all be the same because it's the same shape. But actually, if we work out the details, this time the area would be 10 times 10, which is 100. And the perimeter would be all the way around, I guess 10 plus 10 plus 10 plus 10 is 40. All right, and so this time, area divided by perimeter would be 100 divided by 40, which I don't especially care what this is, but if you were to say simplify the fraction, that's the same as 10 over 4, and you could divide out a 2, that would be 5 over 2 if you fully reduce the fraction. And this is 2, if you divide 5 divided by 2, this is 2.5, right? 5 divided by 2 is 2.5. Anyway, what I'm trying to indicate here is look, we got different answers both times, and this is why I say this fraction a over p is not great geometrically. What I mean by that is you can take the same shape and get 2 different answers just depending on how big it is, and this is not an ideal situation. We would like for this fraction that we're using to give me the same answer no matter what the shape is. I don't care how big it is. I'm trying to measure how weird the shape is. All right, this is just not a good measurement for that because I'm getting this 2 different answers for the same shape. It turns out, and this is kind of a cute fact, all of this problem magically goes away. So instead, we use a divided by p squared. It turns out this actually works exactly the way you would want it to work in terms of changing or not changing when you make the shape bigger, all right? We don't need to get into why exactly this works where the other one doesn't, but I would say the real issue is just in terms of dimensions. The area is a 2-dimensional thing, whereas the perimeter is like a 1-dimensional thing because it's just about distances. And so when you make this fraction, a divided by p, there's something a little weird about dividing. If you think about units here, this is something in square centimeters divided by centimeters, whereas here the units would be the same because I'm squaring on the bottom and I get square things on both sides. Anyway, this one is better. Check it out. If I just draw these shapes again, 1, here the area was 1, the perimeter was 4, and so a over p squared is 1 over 16, right? P being 4, 4 squared is 16. Whereas what about the big one? The big one had 10s, Here the area, remember, was 100 and the p was 40. And this time, if I do a divided by p squared, it's going to be 100 divided by 40 squared is 1600. And if you reduce the fraction, you get 1 over 16, which is the same answer. All right. So the moral of the story is a over p is actually not a very good thing to use to measure how weird the shape is, because you get different answers even if you have the same shape. But a over p squared magically works even for big or small versions of the same shape to get the same answer, which is what we want. All right. Now this, unfortunately, one more slight technicality. So actually, here is the real definition. I'm going to write it as IQ for isoperimetric quotient is defined like, and this I suppose is like the formula you should memorize. It's not all that complicated. 4 pi times a over p squared. All right. Why the 4 pi? Because mathematicians like things which have pi's in them. I will say a little bit about the 4 pi, but let me just clarify here, just in case you haven't got it yet, where a is the area and p is the perimeter. All right. What's the purpose of the 4 pi? The 4 pi, you know, pi is this special number from geometry, and the whole point of pi is that pi is a relationship between the diameter of a circle and the circumference, which is the perimeter of a circle. So the 4 pi here has to do with the perimeter of a circle. The 4 pi makes it so that a perfect circle, come on now, circle has IQ equal to 1. So according to the isoperimetric quotient, the best possible picture or the best possible shape would just be a perfect circle. And then anything else, which is not like a circle but sort of wiggly and wobbly or has more perimeter, would be closer to 0. So the 4 pi makes it so that a perfect circle has IQ equal 1, and this is the best possible. It's actually, there is no shape which has an IQ better than 1. 1 is the best. And then a weird, wormy shape with lots of perimeter has IQ close to 0. All right. So 1 is the best, and that, because of the 4 pi there, that will be achieved by a circle, a perfect circle. And 0 is, in theory, the worst. This fraction can never exactly equal 0, but it can be pretty close to 0 if it has a lot of, if your shape has a lot of perimeter. All right. And this, you know, you get a fraction here. You can write it as a percentage if you like. I just thought, as far as like what in real life, what is sort of a good shape versus a bad shape in terms of the isoperimetric quotient. So I looked this up. If you look nationwide at the U.S. Congress districts, the U.S. House of Representative districts have an average isoperimetric quotient of 0.23. All right, so 1 is the theoretical best. In real life, you usually don't get close to 1. Like 1 would be a perfect circle, and of course, on real maps, the districts are never perfect circles. More likely, you will have something, you know, in between 0 and 1, and this 0.23 is the average. So the average is actually pretty low. So if your isoperimetric quotient is, say, 0.5, that's actually pretty good, because the average would be that's above average, right? This is the average for the houses. All right. let's just do some examples. Actually, if I show you a district and ask you to find the isoperimetric quotient, it's not so hard to do. You have to be able to find the area, which you can do by counting dots like we did last time, and also the perimeter. Unfortunately, this perimeter is a little hard to calculate. So for a, I will say sort of like real life shape, the perimeter is hard to measure. We can measure the area like we did last time by counting the dots, but actually the perimeter, the distance around the edge, you can't measure by laying dots on top. There isn't a similar sort of simple technique. For real life shapes, the perimeter is hard to measure, but it's actually easy for, I will say it like grid-based shapes. And I have some like that for us to try. So I got another handout. These are a bunch of grid type shapes, gritty, if you will. Everybody loves gritty. All right, everybody got one? So we have here 6 shapes. Let's just try to find the isoperimetric quotient of each one. Maybe I'll do the first 2 and then I'll have you all try the others. And that'll be about it. And you'll find, I hope you'll find, this is not very difficult. So I have this one here. Let's look at, so I'm holding it this way around. Let's look at the one in the upper left corner. I'm referring to, just the shape which looks kind of like an upside down umbrella of the formed by the black squares. All right, so to find the isoperimetric quotient, we must count the area and also the perimeter, and then you just do 4 pi times the area divided by the perimeter squared. So in order to find the area, I'm just going to count the boxes, right? That's what the area is. So it's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. All right? So the area of this thing is 23 because I counted up 23 individual boxes there. And now, what's the perimeter? Remember, the perimeter is the distance around the outside. So this is the perimeter. If you wanted to, if you know what you're doing, it's not really necessary to draw in the perimeter, but this is what we're talking about here, is the perimeter. And then, how long is that? Well, you can just count like the side lengths as I go around. So I'm going to mark off also, maybe I'm going to start right here, and then just go around the circle and count off the individual lengths. So I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 29, 30, 31, 32, 33, 34, 35, 36 is what I get for the perimeter. I am counting the length of that blue line as you go around. Counting it just sort of one by one. And you have to like go around all the little corners. But anyway, what did I say? 36? I think I said 36. So the perimeter is 36. All right. That's all the work that you need to do. What's the isoperimetric quotient? You just use the formula, and I hope everybody remembers the formula. The isoperimetric quotient is 4 pi a over p squared. That would be 4 pi times 23 divided by 36 squared. And if you were doing this on one of our tests, you would just leave your answer like that because you're not going to be able to multiply or even square that. I mean, you could by hand if you really wanted to, but I don't care about that. All right, so this one, just for fun, I plugged it into my calculator just so we can compare. I got 0.223 when I plugged all of that into my calculator. On the homework, I might ask you to plug it into your calculator. All right, this is that's how we do it. Any questions about how I did that? Let's try this one on the other side, and then I'll have you guys try the others. So first, I'm going to count up the area. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. When you know what you're doing, I think this is pretty straightforward. And the perimeter. So that's all the way around the outer edge, going around all the corners and such. I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. The perimeter is 20. All right. Unlike counting the dots, you should be getting exactly the same answers that I get here. There's no like ambiguity about something is on the line or over the line or whatever. Okay, so my real answer for this one would be the isoperimetric quotient is 4 pi times a, that's 13, divided by 20 squared. And this I put in my calculator, I got 0.408. All right. It means, so remember, like what do these numbers represent? It means that this shape on the right-hand side is like a better shape according to the isoperimetric quotient. It is a less weird and wiggly shape. And the one on the left is more weird and wiggly according to the isoperimetric quotient. All right, can I have you guys try these other ones? See what you think. Do the same stuff. You should get, and you can plug into your calculators on your phone if you want. You should get an actual decimal number for each one. Yeah, I mean, you have to be counting up the distance around the shape. Yeah, even though it's going to be off. It's not that. All right. Calculating. I'll give you a few more moments.
Is that right? That's how we calculate it.
Yes, yeah.
Okay.
Do you not feel good about it?
Well, I just want to
these, the answers you get, like seeing my answers for the first two.
Yeah, okay, so it looks relevant, yeah.
It should always be between 0 and 1. If it's outside of that range, you definitely get it wrong. Stupid here. Calculating. Okay, still good? You can just use like 321 for.
Wait, there's no pi button. There is?
I think maybe there is, but you can just use 321
I think it's like if you go.
Yeah, if you go sideways.
And like there's one. Is this the one?
Yes.
Oh.
Like if this was on a test or something, you just leave it like that. Although I wanted to calculate them just so I can compare one to another.
Wait, so then you can. Yeah. Wait, so then you do 4. I'm sorry.
All right, I'll tell you what I got for these. So for the kind of like tall boy on the left there, I got 7 and 16, which when I plugged into my formula, I get 4 pi times 7 divided by 16 squared. All of this you can do on your like iPhone calculator. There is a pi button if you turn it sideways. Anyway, I plugged all of this in and I got 0.343 something. I hope that's what you got when you plugged it in. Any master pluggers out there? I think people got this. Okay, this one I got 11 and 24 when I plugged in the formula here. So it's 4 pi times 11 divided by 24 squared, and this was 0.239. All right. Anybody agree or disagree? That's what I got. That's all I'm saying. I suppose I'm just as likely to mess up the calculator step as you are. This one here, I got an area of 14 and a perimeter of 20, which gave me the IQ of 0.439. And then the one on the bottom right corner, I got 21 for the area and 32 for the perimeter. So like I said, you should be getting exactly the same values here as I am if you're doing it right. Although it is, it's easy to mess it up a little bit. And then when I plugged that one in, I got 0.257 for the isoperimetric quotient. All right. This is a specific measure of how weird the shape is. Any questions about any of those? I hope that you got something like that. All right. So if I were looking at all of these together, according to the isoperimetric quotient, sort of like the best one, I guess, is this one here, right? Because this has the greatest IQ. Remember, the IQ could, in theory, be from 0 to 1. 1 is like the theoretical best, although 1 is pretty hard to achieve in reality. 1 is only achievable if you have a perfect circle. So this would be the best, and the worst, I guess, would be this one, which has the smallest number, 0.223. All right. Any questions about that? This is the isoperimetric quotient. I think in order to do the isoperimetric quotient is really not too hard as long as you know what you're doing. All right. I have just one last thing to say about this, and then we got some time. We can move on to something completely different. My one last thing to say about this is, I will just say, note, the IQ is different from the convex hull ratio, which is what we talked about before. All right? These are just two different measures. They are two different, really they're sort of like two different ideas about weirdness of a shape. And the concept of a shape being weird or not is a complicated concept, and there are different ways of judging the weirdness of a shape. One is the convex hull ratio and one is the isoperimetric quotient, and they can give you different answers, and actually they can give you, in some cases, like very different answers. For example, this long, tall, skinny one that we did, this had, on the paper there, this had isoperimetric quotient equals 0.343, right? That was one of the ones that we just did, the tall, skinny one. But what if we were to do the convex hull ratio of this thing? But the convex hull ratio, remember what that one was? It was the area, it was the a fraction where you take the original area divided by the convex hull area, right? This is what we were doing last time. But check it out, this shape here is already convex. If I were trying to do the convex hull thing, that's the one where you add in straight lines to fill in any inward curves. There are no inward curves on this. This is just a tall, skinny rectangle. All right. So actually, in this example, the original area and the convex hull area are the same because this shape is already convex. There is no extra stuff to add in. So the convex hull ratio, actually for that one, is a perfect 1. This, according to the convex hull ratio, is perfect. Whereas this is not so great. I mean, it's definitely not perfect, which would be 1, right? So this is, I would say, not perfect. All right. The moral of the story is these two things, they are just measuring two different things. And it is possible for a shape to have a very good convex hull score, but a bad isoperimetric quotient score. That is possible. And this is a good example of that. It's because this shape is convex, even so it has a big perimeter, which makes the IQ not close to 1. All right? They are just two different things. And so if you're doing real-life analysis of gerrymanders, they typically use several different measures. And these are 2 of them. There's actually more than this. There's even more than just these 2 measurements. There are many ways that you can make similar types of measurements using different mathematical ideas. These are probably the 2 simplest ways to do it. There are much more complicated ones, though, if you're into that. All right. Here ends the discussion of the isoperimetric quotient, and here ends the entire, this big unit in the course, which has all been about gerrymandering and also the other voting type stuff. Maybe now would be a good time to remind you all that our next test is going to be next week on Friday, so that's a little something to look forward to. As before, the test will include a question on every topic, even the super old ones, and so I hope you're all keeping up with your checklist after the previous test. You should know which ones you have already got full credit on, and only do those ones on the test. I'll say more about the test as we get closer, although, to be honest, I don't have a lot to say about it. It's just going to be what I just said. All the old ones plus some new ones. All right. Great. Let's talk about something completely different. So if you look at our big checklist here, we now have finished the gerrymandering unit. Number 16 on the big list was isoperimetric quotient. Our next little unit of 3 topics is something completely different, and it's called, we might as well get it started. We got 15 minutes remaining. It's called fair division. This is a little fresh start. Fair division has nothing to do with what we've been talking about, anything that we've been talking about so far. Although I put it next to the gerrymandering because it is also vaguely geometric, maybe even a little more geometric. I don't know. Fair division, though. This is something that is, I think, a super interesting mathematical thing that people work on. Although, to be honest, I was surprised when I first learned about this. I was surprised that anybody even cares about this, or that this is something that mathematicians have focused so much time on. But this is about dividing an object fairly between 2 or more people. Dividing an object. This is like if you and your roommate are sharing a cookie. What's the best way for you to split it up between the two of you? All right? Now, if it's just a cookie, the best way is probably you just cut it in half and you each take half. That's how you share a cookie. That's not very interesting, but things become more interesting. So I'm going to say this is most interesting when the object is, I will say, non-uniform. What I mean by that is the thing that you're trying to divide is not just like all the same, all parts of it are the same. For example, I remember when I was a kid and I went to like my friends' birthday parties, they would always have the birthday cake and it would be like decorated with, so it was like the classic example would be like, it'd have kind of like flowers around the edge made of frosting, right? And I don't know if this is still the case on these mean streets. Among my friends, everybody wanted the flower in the frosting. Not because we were into flowers, but because we were into frosting. And so, this is an example where, okay, it is just like a big cake, and you could, on some level, just say, well, I'm just going to cut it up into a bunch of equal pieces. But those pieces are not actually equal because some of them have the flower, and that's better, all right? That's what I mean by non-uniform. That is to say the object, this is most interesting when the object somehow has like some parts of it are better than the other parts, but you still have to think of how to divide it fairly, all right? So it's most interesting when the object is non-uniform and when the people have different values. This is actually very realistic in terms of trying to do this in important situations in real life. When the people have different values, this is like if I have a tray of brownies. We could try to do this in this room, actually. If I have a bunch of brownies and I want to divide it fairly between all of us, it is not good enough to just cut them in equal pieces because, anyone know what I'm getting at here with the different values? This is a discussion that always arises when you are sharing brownies with your friends. Some people like the edge, some people like the corner, and some people like the middle, right? So when the people have different values, this complicates matters. Is it still possible for me to make equally fair pieces if like some of you don't like the edge piece, but some of you do like the edge piece? Is it actually possible to divide it in a way that everybody will be satisfied? That's the kind of situation that we're going to be talking about. When the object has different features and the people have different values about how they value the object. This, on some level, it sounds stupid because I'm just talking about like cake cutting. Sometimes this is referred to as mathematical cake cutting problems. But situations like this happen all the time in the real life. So there were similar issues actually like in, this is like the most realist of the real life. This sort of thing happened when, like they talked about dividing up Europe after World War II, right? All the countries that had been conquered by Germany were kind of like distributed, like the maps were just sort of cut up. It was like, okay, France is going to keep this stuff. This stuff is going to be organized and run by the UK and the US. This stuff is going to be organized and run by the Soviet Union. And that's how we had like East and West Germany were separate places. But, and lots of other, Poland, it was decided that the Soviet Union would get control of Poland. All of these things were a very fancy type of cutting up the brownie. And there were several different players involved, and they all had different values about like, we want cities that have good manufacturing ports or something, and other people wanted other things. And anyway, it was exactly the same situation. All the people were trying to get something different out of the situation. They had different values, and of course the various territories had different values to them. All right, so anyway, here is, I'm just trying to say this is super important. You could also think of something like This is not exactly the same, but it's like after, after getting divorced, like people have to split up all their stuff, and it's like, we have to decide who gets the TV, who gets the couch, and it's like I might have a different opinion about the couch than my wife does. So there are like different values that different people are assigning to different objects. It's the same kind of a situation. So it happened after World War II, I will just say, etc. This actually happens all the time in real life. And in real life, when you're doing this, usually it is the case that people have different values about what they want, but you still want to do something that everybody feels like is fair, all right? Okay, let's talk. I got a very specific example. So we are usually going to talk about kind of simple examples. Let's talk about, this is a picture of what they call the Neapolitan ice cream. That's the one which has the strawberry, chocolate, and vanilla all together. You know what I'm talking about? So let's say, and it's usually like in 3 stripes here. So let's say this is the carton of ice cream, and let's say they're arranged this way: strawberry, chocolate, and vanilla, like that. All right. And let's imagine that you and me are trying to divide this fairly between the two of us. All right. Now you might say, can't we just cut it right down the middle and then we each choose a piece? This is not necessarily going to work very well because we have different values. So let's say that I like the vanilla, I hate the chocolate, no, I hate the strawberry, and the chocolate is okay in my opinion, all right? So these are my values. I'm telling you which ones I like and don't like. And then let's imagine that you like all of them equally, all right? You don't care about vanilla, strawberry, chocolate. This, by the way, is more or less my true opinion about the Neapolitan ice cream. And I don't know about you. I kind of dislike the whole idea. I don't like you put the 2 flavors right next to each other. No. I go to the store, I buy the flavor I want. I don't want 3 different things in stripes. But anyway, let's just say this is how we all feel about the situation. Now, there's only 2 of us. Actually, there is a tried and true method which works for 2 people so that everybody feels good about the result. And that is, for 2 people, this is how we did it in my house growing up with my sisters. We do what me and my sister called you cut, I pick. So I'm sure you're familiar with this general strategy. It means one person decides to divide it in half. Now, it may not be straight down the middle, like I said, because we have different values about everything, but one person divides, I will just say specifically what I mean by this. One person divides into 2 pieces. Which seem equal to them. I don't mean equal size, but like equally valuable in their opinion, all right? Remember, everybody has their own different opinions about what's valuable, but the idea is one person divides the thing into 2 pieces which seem equal to them, and then the other chooses to keep one of these pieces, and then the first one takes the other piece. I cut, you pick, or you cut, I pick. This is how we were always instructed to share things when I was a kid with my sister. All right? One person divides into 2 pieces which seem equal in their opinion. The other person chooses to keep one or the other of them. And then the first one gets to take the one that was not chosen. All right, so can we just try this same example and see what would happen? So this is what we're talking about here. strawberry, chocolate, vanilla, like that. All right? And let's just imagine what would happen if we did this in real life. So let's say you cut. Remember, I said at the beginning, your values, I will just remind us, I like the vanilla the best, I hate the strawberry, and chocolate is okay, right? You like all equally. All right, now, if you're going to be the cutter, I would say if you cut and you like them all equally, your cut would probably, you really could just sort of cut right down the middle, right? Because you like everything equally. You might as well, if you're going to divide it into two halves, which seem fair to you, and you like everything equally, you might as well just go straight down the middle, right? You could have also gone, straight across the middle this way, I suppose. There are lots of ways you could decide to cut it down the middle, but this is the most sensible way. All right, so you cut like that. Okay, given this cut, which one will I pick? So I'm going to draw this again. I'm trying to draw it like in stages here. First, you cut, and now I pick. Which side would I pick? This is the strawberry, the chocolate, the vanilla. You may be tempted to say, well, they're both equal sides, so you pick whichever one you want. It's not true, actually, because of my values. Which one am I going to pick? Yeah?
The chocolate and vanilla.
The chocolate and vanilla side, yeah, the one on the right, because of my values that I said before. I like the vanilla. I hate the strawberry. The chocolate is okay. So I'm going to try to avoid the strawberry part. I'm going to take the vanilla part and half of the chocolate. So now I pick this one, right? This half. And then you get the other side. Now I pick this one. You get the other. So our final sort of division looks like, here's the original thing. It had the three sections like this. But anyway, there was a cut right down the middle. This here is my piece. And this here is your piece. All right? That's our final answer as far as how it was cut. All right? Just one last thing to say before we leave. Can we say, after all is said and done, does this actually look fair for both people? Your piece versus my piece. So I think you view this as fair because, in your opinion, everything is equally valuable and you got half of it, so that's fair, right? So you view this as fair because you got half. And it's all equally valuable. To you, right? This is all about people's differing opinions about the value. So your piece to you seems fair. It seems to be like exactly half of the total value. What about my piece to me? It's actually a little bit different. Anybody feel it? I think my piece, I would view my piece as fair. It's time to go now. Actually, when I look at this, it seems to me I'm getting even better than half of the value here because I hate the stuff on the left anyway, right? So I'm feeling real good about this. I got the part that I like and I avoided the part that I didn't like. So you view this as fair. Actually, to you, this is like an even 50-50 split. To me, actually, it's even better than that because I'm getting the good part and you're getting the bad part. That doesn't make it unfair for you because you don't think it's the bad part to you. So you view this as fair. I view my own piece as even better than yours. So it's, in my opinion, actually better than fair. All right? I say this is a good result for both of us. For you, it's even. For me, it's actually even better than that. All right, more on this next time. The big question is, how can we do this with 3 people? It's quite a bit more complicated. That's where we're going with this. Let's see if our